Target Encoding without leakage is cool. StatQuest. Hello, I'm Josh Starmer, and welcome to the StatQuest live stream. I'm super excited to be here, and I hope you're excited to be here too. I'm going to put my ukulele on the floor so that I don't drop it while I'm talking. Also, I want to apologize because I know the last time we did a live stream, I said that I was going to play the tabla, those things on the big harmonium behind me, and I was like, it was like 2 weeks ago, right? And so I was thinking, I got plenty of time. I've got lots of stuff to do, so I'll just wait to practice the tabla until a few days before the live stream, and it'll be awesome. Well, I got to a few days before the live stream, and I was like, I've got so much to do. This is crazy. And so I didn't have any time to practice the tabla. And this is bad because people even reminded me. I got little notes in the comments like, hey, don't forget to practice the tabla, and I was thinking about it. I just didn't do it. And so maybe we'll do it next time. I've also, it's hilarious. I also have a tambura that maybe I'll bust out and tune that up, and I'll see if I can get a friend to come and play that. Give me a little drone in the background. That'd be pretty cool, I think. Anyways, welcome everyone here. I'm really excited. I'm just looking at the comments right now. So it looks like someone's got a job interview tomorrow. Good luck. I hope this is helpful. And I'm glad you like the new song. I actually kind of messed it up because I was gonna so the song, I had it all planned out. Not that I practiced it at all, but I had this plan, and and what I was gonna do, I was gonna say Target Encoding without leakage is cool. So I was gonna do like a gap when I said without. So it'd be like without what? Without music, without any sound. It's gonna be like a little play on the word without, kind of musically. And that didn't happen. But it's a thought that counts. So anyways, without further ado, I'm really excited you guys are here. Let's dive into target encoding without leakage. Which, to be honest, sounds kind of gross, right? So, maybe not the most nice topics to bring up with your parents or whatever. So anyways, without further ado, let's talk about target encoding without leakage. Oh, by the way, feel free to post questions in the chat. I won't read them while I'm doing this because I can't see them and read and go through the StatQuest at the same time. But at the end, if we have time, and I hope we have time, I'll go back and read the questions and I'll get to some of them. I won't get to all of them. I'll read all of them though. So even after the live stream is over, I leave the window open for a little bit so I can read all the questions that people have, and hopefully we can get to them next time. All right. So for the third time, without any more further ado, we're going to talk about target encoding without leakage. Beep. Okay, so first, let's review some basic encoding strategies. Because we talked last time we did a live stream, we talked about target encoding. So we're just going to do a quick review of the basic strategies. So when we first talked about target encoding, we had this data and we wanted to use favorite color, beep, and height, boop, to predict if someone loves Troll 2, which is a really terrible movie. In this case, a favorite color has 3 discrete values: blue, red, and green. Now, in theory, discrete features like a favorite color are fine for most machine learning algorithms. But in practice, a lot of popular machine learning algorithms, including neural networks, do not work well with them. As a result, discrete data are often converted into numerical values before being used for machine learning. One excuse me, golly, I'm getting ahead of myself. When we don't have many discrete options, one-hot encoding is commonly used. And we talked about this last time. So we're just going to like, boop, we're just going to go right through it real fast. Boop. But the problem with one-hot encoding is that it adds columns to the data set. In this case, we replaced the favorite color column with 3 columns, one for each color. And that's not a big deal. You know, our data set's a little bigger than before, but it's not like overwhelmingly huge. However, when we have a lot of options, for example, if we had a column of postal codes and there are 41,683 postal codes in the United States, whoop, what happened? Then we would end up replacing the one postal code column with 41,683 new columns, which might make the data difficult to work with. So when there are tons of options, instead of using one-hot encoding, people often use target encoding. One of the most popular target encoding strategies is to replace each option. Oh, I just like, there's a disclaimer. This morning I woke up at 1 a.m. and could not fall back asleep. I guess I was excited about the live stream. I don't know. But I've been up for a long time and I'm a little sleepy. So I've got a feeling I'm just going to be like saying all kinds of weird things. So stay tuned. Anyways, back to the StatQuest. So one of the most popular target encoding strategies is to replace each option with a weighted mean of the target, the thing we want to predict. Boop. For example, in order to use target encoding with our data, we start by plugging the mean of the target for blue, 1 divided by 3. Then, because 3 people were used to calculate the mean for blue, we plug in 3 for n. Beep, beep. Then we plug in the overall mean for the target. And by the way, the target is Love's Troll 2, which is 3 divided by 7 because overall 3 of the 7 people love Troll 2. Beep. Now we just need to pick a value for m, the weight for the overall mean. M is a user-defined parameter or hyperparameter, and in this example, we'll set m equal to 2. Beep, beep. Setting m equal to 2 means that we need at least 3 rows of data before the option mean, the mean we calculated for blue, becomes more important than the overall mean. Now we just do the math and we get 0.37. So we plug in 0.37 for blue. Beep. Now we calculate the weighted mean for red. Boop, 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 boop. Beep, boop, 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 boop. And we get 0.29. So we plug in 0.29 for red. Beep. Lastly, we calculate the weighted mean for green. And we get 0.57. So we plug in 0.57 for green. Anyways, I got ahead of myself here. So we'll just say, bam, that's exciting. But anyways, note, some of you may have noticed that we are using the target, the thing we want to predict, to modify the values in favorite color. And doing this sort of thing is a data science no-no that we call leakage. Leakage results in models that work great with training data, but not so well with testing data. So anyways, because we're using the target, which is Love's Troll 2, to modify the values under the favorite color column, we're creating some sort of, we're kind of establishing a relationship between the ones and zeros in Love's Troll 2 and the numbers we get in favorite column. And that relationship is going to mean we're probably going to overfit this training data. So in other words, leakage results in models that are overfit. The good news is that there are a bunch of relatively simple ways to avoid leakage so that you can use target encoding without overfitting your model. So let's go back to the original dataset that had blue, red, and green categories for favorite color, and talk about k-fold target encoding, which is probably the most commonly used method that avoids leakage. Note, the word fold in k-fold target encoding refers to splitting the data into equal-sized subsets. And the k refers to how many subsets we create. For example, if we did two-fold target encoding, then we would divide the data into two equal-sized subsets. Boop. Note, because we have an uneven number of rows, we just made the subsets as similar in size as possible. So we have one subset with 4 and the other subset with 3. Good enough. Okay, now to make it easier to keep track of things, let's label the first subset A and the second subset B. Now, to target encode blue in subset A, we ignore the target values in this subset and instead plug the target values from subset B into the weighted mean equation. We start by plugging the subset B mean of the target for blue, 0 divided by 1, because one person in subset B that likes blue, because the one person in subset B that likes blue does not love Troll 2. So it's 0 divided by 1. Then, because there's only one person in subset B that likes blue, we plug 1 in for n. Beep, boop. Then we plug in the overall mean for the target in subset B, 1 divided by 3. Because, overall, one of the 3 people in subset B loves Troll 2, or only one. And just like before, we'll set m equal to 2, which means we need at least 3 rows of data before the option mean, the mean we calculated for blue, becomes more important than the overall mean. Boop, boop. Now we just do the math and we get 0.22. So we plug in 0.22 for the 2 rows in subset A with blue. Now we need to target encode the 1 row with blue in subset B. So we ignore the target values in this subset and instead plug the target values from subset A into the equation for the weighted mean. So we plug in the subset A option mean for blue 1/2. N equals 2 because we've got 2 rows with blue in subset A. And the overall mean 2 divided by 4 because 2 of the people in subset A, 2 of the 4 people love Troll 2. Beep. And just like before, we set m equal to 2. Boop, boop. Then we do the math and get 0.5. So we plug in 0.5 for blue, but only in subset B. Beep. Note, you may have noticed that the different subsets have different values for blue. So in subset A, we've got 0.22 for blue, and in subset B, we've got 0.5. This is okay, because favorite color is becoming a continuous variable just like height. Now let's encode the color red in subset A. So we ignore the target values in subset A, and instead plug the target values from subset B into the equation for the weighted mean. Now, because subset B doesn't have anyone who likes the color red, the mean for red is 0. And n equals 0 because there's no one who likes red. And the other values are the same as before. Boop, boop, boop. And we end up with replacing red in subset A with 0.33. Likewise, green in subset A uses the target values in subset B and turns into 0.42. Boop. And green in subset B uses the target values from subset A and turns into 0.67. Boop. Now that each color in each subset has been encoded, we merge the subsets back together. Boop. And we're done. Hooray! Bam! Now, going back to the original data with blue, red, and green, if we set k equal to 7, because remember we're doing k-fold target encoding, then we would divide that data into 7 subsets. Now, to target encode the first subset, which consists of a single row with favorite color equal to blue, we ignore its target value and use the target values from all of the other subsets to calculate the weighted mean. Likewise, encoding the other subsets would use all of the other target values except for their own. Boop. Note, when we use all of the target values except one to do the encoding, it's called leave one out target encoding. A quick scan of the internet shows that some people are successful with this leave one out target encoding. And other people are successful setting k equal to 5, so using 5 subsets. So if you have a lot of data, you can split it into 5. So I've seen both things, and I've seen people say that they've had great success with Kaggle competitions using both methods. So yeah, you can try them both. Double bam! Now that we understand the most common ways to do target encoding without leakage, let's talk about a relatively unique approach used by an algorithm called CatBoost. So people have been asking me to cover CatBoost for forever. And right now, right here, is my very first little foray into CatBoost. So you guys are the first to see it. I guess you're the first to see everything today. It's all brand new. But this is like something people have been asking me for years. And so, cool that you guys are here right now, I guess. Okay, so first, let's go back to the original data set with blue, red, and green. And instead of splitting the data into subsets, CatBoost treats each sample as if it were fed into the algorithm sequentially. For example, CatBoost treats the first row with blue as if that is all the data it has received so far. And that means CatBoost ignores all the other rows when target encoding blue, or not just all blues, this specific blue. I should be clear there that we're not talking about all the blues. We're just talking about the blue in the first row. And when it's encoding that blue, that specific one, it ignores every other row. Another thing different about CatBoost is the equation. I got this equation from the documentation. If you look in the manuscript, the original manuscript, they have a different equation that's actually identical kind of to what we were using before. But in the actual documentation for the implementation, so like, there's like the theory paper, and the theory paper has one equation, and then you go to the user manual for the actual CatBoost, and they have a different equation. This is that different equation. So if you look at the original manuscript, you'll see something different. That's a lot like what we were using before. But if you look online at the documentation of how to actually use CatBoost in practice, you'll see something like this. It won't be exactly like this, but this is equivalent to that. I've chosen to change it a little bit just to show how it's related to what we were doing before. Okay. The big difference is that instead of using an overall mean, it uses a user-defined prior, or guess, that is usually 0.05. To be honest, I don't know what the default value is. I looked in the documentation and I could not find one. But the user documentation has an example of how CatBoost does encoding, and it uses 0.05 in that example. So that's the best I can do, at least for now, unless someone sends me the URL to the documentation that explains where this value is set. Okay, anyways, the CatBoost equation also simplifies the denominator by just adding 1 to the number of rows rather than a weight. Now, given the equation, CatBoost plugs in values derived from all of the data that came before the current row. And this is key. This is the thing that makes CatBoost work and not, this allows it to avoid leakage. Okay. And that means since we are starting with the first row and no data came before it, we plug in 0 divided by 0 for the option mean. So we can only use data that comes before the sequence, the row that we're actually trying to encode. And there's no data before that, so everything's just zeros. And we plug in 0 for n because, yeah, there's no values that came before. And when we do the math, we get 0.05. So we plug in 0.05 for blue in the first row. Boop. Now we work on the second row. Because none of the preceding rows have red as the favorite color, we set the option mean to 0, 0 again. And again, n equals 0. Boop. So we replace red in the second row with 0.05. So just like we did for the blue. Likewise, we replace green in the third row with 0.05. Again, we do this because none of the preceding rows also have favorite color equal to green. However, in the fourth row, things finally change. Now, because we've seen blue before in the first row, we use it to calculate the option mean. Psst, remember, we only use the rows that came before the one we were working on in the equation. So we just use the first instance of blue in this case. So in this case, because the one person who liked blue before also liked troll 2, the option mean is 1 divided by 1. Boop. And n equals 1. Boop. So we plug in 0.525 for the second time we see blue. Beep. Likewise, the second time we see green, we plug in 0.525. Beep. However, the third time we see green, we use the 2 previous times when calculating the option mean. And the option mean is 2 divided by 2 because both of the 2 previous people that liked green also liked troll 2. Beep. And that means we replace the third occurrence of green with 0.683. Lastly, we replace the third occurrence of blue with 0.35. Beep. Because only one of the 2 previous times we saw blue also liked troll 2. And thus, this is how CatBoost performs target encoding. And because the order of the data makes a difference in the encoding, this method is called ordered target encoding. Actually, they in the manuscript, the original manuscript, they call it ordered target statistics, but everybody else calls it target encoding. So we're just going to call it ordered target encoding. It's much more common to call it target encoding. All right. So bam. So why the small bam? Because the justification that CatBoost provides for why it does things this way, instead of just using leave one out encoding, doesn't make any sense. The authors of CatBoost claim that when there's only one option, like blue, so what you see here, instead of having blue, red, and green, all we have is blue. Blue, 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 blue. Okay, we got a ton of blue. So the authors claim that when you only have one option, like blue, then leave one out target encoding results in leakage. And thus, you should not ever use leave one out target encoding. To their credit, the thing about leakage is true. When we only have one option, like blue in this case, then leave one out target encoding does, in fact, result in leakage. But regardless of whether or not it even makes sense to include a column with a constant value in the model, when we only have one or two options, everyone, including the CatBoost algorithm itself, uses one hot encoding. Boop. So we just change everything to one. We don't actually do leave one out target encoding because there's no reason to do it. You just replace it with one. If you even leave the column in your data set, you probably should take it out. So the leakage problem with only one option turns out to not be a problem because it's like no one would ever do this, right? And CatBoost itself doesn't even do it. I mean, nobody does this. When there's only one or two choices, you use target encoding because it does not increase the number of columns in your data set. It's just like what we did with Love's Troll 2. We had two options. We had yes and no, and we turned those into ones and zeros. It's no big deal. So I'm not actually convinced that leave one out target encoding is a huge evil thing that is going to cause problems all the time. And in fact, tons of people use it all the time and are very successful. So I'm a little annoyed that they gave such a lame reason for using such a bizarre way to code categorical options. So yeah, this is what CatBoost does, but I don't think it's really justified. Wah, wah. However, rather than end on a sour note, the important thing is that regardless of the justification, CatBoost works, and it works well. And that's an important lesson about machine learning. Unlike math, where every little thing can be logically derived and has a pure beauty, machine learning is all about results and doing whatever it takes to get them. And sometimes that means getting a little messy. So triple bam. Hooray. So yeah, we've talked about CatBoost without leakage, and we've talked about target encoding without leakage, and we've also started to talk about CatBoost, and I'm thinking we might just keep talking about CatBoost until we fully understand that algorithm, which is kind of tricky because the documentation is not great, and the manuscript and how it's actually implemented are kind of different. So it's kind of tough, and it's hard to be confident that I know what I'm talking about because I see from the same source, I see two different messages. But that is the plan. We're just going to stick with this for a little while and see how far it goes. So without further ado, let's just open this up to an AMA, which is Ask Me Anything. And what I'm going to do is I'm going to go through the comments and I'm going to see if we have any questions about what we just went through. Someone asked, will this session be recorded and available on my channel? And the answer is yes. So that was an easy question to answer. So someone else said, what happened when we are using the model for inference on unseen data? In that case, we don't have the target. And how are we going to apply k-fold target encoding? So what you do is when you're not training. So when you're not training, what you do is you can then just use all of the data to figure out because there's no leakage in that case, because it's almost like we're doing leave one out with our new sample. Does that make sense? So when we did leave one out target encoding, we took one row and we used all of the other data to encode it. Likewise, when we get new data and we're trying to classify it, we don't actually even know what the target is. We we then use all the other data that we used training wise to encode it. So that's how that works. Bam. So someone asked, what if there are lots of similar values, but not all in the column? Does it still cause leakage? And I'll be honest, I don't understand that question. Wah, wah. Kumar, if you can clarify, that might help. Maybe I can do that. Anyways, what else? Do you guys have a good weekend? I did. I went for a long walk in the woods. It's fall here, and the trees are turning pretty colors, and I had a nice walk in the woods. Okay. Oh, excuse me. Someone said, "What if target is numeric? So the regression problem." It's the same thing. You just calculate the means. The average. The option mean and the overall mean. It's the same. Nothing changes. So that's easy. So it works either way. So it works for categories and it works for regression. Or excuse me, it works for classification. If you're just joining us, I woke up at 1 a.m. This morning. I have no idea why. Potentially because I was so excited about this live stream. But I've been I've been up for a long time, and my mouth and my brain are doing two very different things, and it's kind of comical. Okay. So someone asked, why is your book very expensive in India? So right now it should not even be available in India. So if you're seeing it for sale, that might be a used copy that someone is marking up the price. That being said, printing in India is not easy. Printing color in India is not easy, nor is it cheap. This is a mystery to me. A total mystery to me. It's been very expensive. That being said, I have contacted a printer in India, and they've printed out some proofs of my book, and they're sending them to a friend of mine who lives in Bangalore. And when he gets the proofs, he's going to look at them and inspect the quality and make sure it's good quality. And if it's good quality, he's going to let me know, and we're going to flip the switch, and we're going to start selling these books in India. They're not going to be super cheap. They're going to cost probably as much as they cost in the US, maybe a little less, but not much less. And there's nothing I can do about it. It's just the cost of printing color in India. So that's sort of a bummer, but it's what it is. So there's that. Oh, someone asked, so some Kumar has rephrased their question. And yeah, so they said, what if you have 50 blues and 3 reds in an example? Well, if you just have 2, again, you can just use, we can just use one hot encoding, but assuming we're going to use target encoding, that's when the overall mean kicks in. It compensates for our lack of knowledge about how red is behaving. And yeah, so you just kind of do it as you would normally do. You don't have to worry really that much about the imbalance in the data. Someone asked if I'll explain what I mean by leakage. Leakage has to do with when information about what we're trying to predict, the specific thing we're trying to predict. So in this case, we'll go back to the keynote. So in this case, we're trying to predict Love's Troll 2. And in this case, 1 represents yes and 0 represents no. So we're trying to predict that. And without using k-folds or leave one out target encoding, or using this CatBoost method target encoding. If we just use the full data set like we did early on to calculate the numbers, that means that this number 1, so in the first row, I got my little pointer. In the first row, that number 1, loves troll 2, would have an impact on the number that we use to encode for the first blue instance of blue. And that influence, so now there's a relationship between this number and this outcome value. And what that means, and that's the leakage right there. And what the result of that is that our model, because it knows about what the output's supposed to be, because favorite color has encoded into it some bit about what troll 2 will be, then we overfit, and we may predict the training data very well, and we'll be like, hooray, this is doing great with our training data. But when we use it with testing data or new data from the wild, our model will probably perform a lot worse than it did early on. And so that's why we avoid leakage. By the way, it's, again, machine learning is very pragmatic. And so just because you have leakage doesn't mean your model is horrible and you should be ashamed of it. If it performs awesome, then it's awesome. That's all there is to it. But generally speaking, trying to avoid leakage improves model performance. Okay, someone asked what my job is. I have 3 jobs. One, I do StatQuest. What you're seeing right now in all the videos, that's my job. The other job I have is I work for Lightning. I've got my Lightning t-shirt on. I work for Lightning, and I am what they call an AI educator. And working for Lightning's super fun. What I love about it is, if you know StatQuest and you know me, you know that what I like to do is to make complicated things easy to understand. So yeah, in a nutshell, I like to make complicated things easy to understand. And what I like about Grid and why it's such a good fit for working there is they like to make complicated things easy to do. And so it's kind of perfect. So they do not specifically, but they do a lot of stuff with neural networks in the cloud. And their goal is to make sort of machine learning and AI super easy to do in the cloud. And this is something that I've wanted to teach. I've wanted to teach how to do AI and machine learning in the cloud because, when I was in school, I always hated that I would learn one thing in my classroom and then I'd go to my job and it would be completely different. My goal is to give you a super realistic, this is how production AI is done, tutorials. And Lightning is helping me with those. And so that's another job. The third job I have is to write books. Some of you have heard of the StatQuest Illustrated Guide to Machine Learning. Some of you have copies, which is awesome. Some of you are waiting very patiently for copies because I've been having a heck of a time rolling out printing all over the world. But we're on the home stretch, and hopefully I'll have that all resolved in the next couple of weeks. But anyways, so I write books, and so I've got the StatQuest Illustrated Guide to Machine Learning, and I've just started the StatQuest Illustrated Guide to Statistics. So those are my 3 jobs. There we go. So what's the next question we see? We say, have you heard about the Optuna API? And the answer to that is no. It's a way to optimize machine learning engines, and I love it so much, so I'll look into it. That sounds cool. Someone else gave me a cute wave, which is cute. What else do we have? If I'm predicting a target value using only categorical variables by one-hot encoding, and I get a large coefficients in the model, what can I do to improve my model other? What else can I do to improve my model? at that point, you might look into some feature engineering. It also depends on the type of model you're using. So you might just try a different type of model. Some models are better with sort of nonlinear interactions than others. So one, try a different model. Two, consider something called feature engineering, and that has to do with sort of combining features to make sort of what do we call them? It has to do with combining features so that you end up with like a new feature that is somehow the product of two others or more, two or more. So you got some options. Okay. What are the different types of encoding techniques used in industry for nominal and ordinal data? That's a good question. It's possible that I'm going to be honest. I think ordinal data is like ranking data, and it's possible that that's just treated like numeric data, and you don't necessarily need to encode it because it does have sort of a linear relationship between, like, say, like you're on a scale of 1 to 10, 1 being the best StatQuest ever and 10 being the worst StatQuest ever. You've got this like linear scale. You may not need to actually encode that one. Someone asked if we can do a session on H2O target encoder estimator. Maybe, probably not. Maybe if H2O contacts me and gives me a lot of free time. We'll see. So someone asked if about the equation that you see here. So we've got n times option mean, and someone says, isn't that just the sum of things? And it is. It is the sum of the times we've got 1 here. So if we're doing it for blue, we might sum the 1, 1, and then 0, so we'd get 2 or something like that. Yeah, so that's just I'm just replacing the sigma. It's debatable as to whether or not this is the best approach to presenting this. This is one of the things about live streams is you kind of get to see StatQuest work in progress. You get to see things in advance, and sometimes you see things a little dirty. And so the motive for leaving it like this was it links us back to the original equation where we had a weighted mean. And we see that this part on the left, n times option mean sort of divided by n, that part of the equation did not change one bit. However, the stuff on the right, adding 0.05 and adding 1, that did change. And so I was trying to emphasize what's similar and what's different, rather than making the equation look completely different using the sigma notation. And the reason why I didn't use the sigma notation to begin with is I wanted to emphasize how this is a weighted mean, and it's a weight between the option and the overall. So that's sort of what I was shooting for. That's sort of what was my mindset between like how I wanted to emphasize things. Someone asked about literature on recommender systems, and the answer is I don't know. I don't actually. This is going to be embarrassing. I actually don't know that much about recommender systems. There may not be that much I need to know, given the other things I know, but I actually don't know. I can't talk to you about details of that, at least not right now. Oh, you were using, so the person that was having trouble was using linear regression. Yeah, linear regression is not going to do well at all with, what do they call it? Oh my gosh. This is where you're seeing Josh Starmer, who woke up at 1 a.m. So I've been awake for almost 11 hours now. So when there are nonlinear relationships, and that's just the first thing that popped in my head. There's probably an easier way to phrase that, between the thing you want to predict and the thing you're using to predict, linear regression cannot work in that situation. So I would say that's a good reason to use a different model. Use a decision tree. See if that works better. Because decision trees are great, or a random forest, or one of these boosting models. Use CatBoost. These things are great for these nonlinear relationships, or what else do they call it? Interactions. Sometimes they're called interactions. So there you go. Someone said, William Henry said, Squatch is a great protagonist in my book. Thank you very much. Hooray. Someone asked about common feature engineering techniques. One is just sort of like normalizing. This encoding is a feature engineering technique. So normalizing, those are all kind of standard, no-brainer type feature engineering things. Others are just, golly, can't think of anything off the top of my head that's not specific to the data type. Like sometimes you can add columns together, add the values together, or multiply the values together, or join them in some kind of interesting way that makes sense. Oftentimes there's ratios are useful for feature engineering. So it may be that the ratio of two of your features is really good at predicting Love's Troll 2. So that's another useful way to do feature engineering. Someone asked when spectral clustering will outperform k-means clustering. And the answer to that is, this is going to sound embarrassing, but it's honest. I actually don't understand how spectral clustering works. That's something I just haven't gone into much on my own. So I can't answer that one. Someone asked where they can purchase my book, and that really depends on where you are in the world. A lot of the places outside of India, specifically, you can use Amazon. If you're in Europe, if you're in North America, you can use Amazon. In India, I hope to make an announcement in 1 or 2 weeks about where you can get it there. I'm going to have an online retailer in India that will sell you the book at sort of the best price that I can wrangle in India. But you won't find out for a little bit. I'm also working on getting the book published in India, and hopefully we'll get not India. Golly, this is embarrassing how much I'm messing things up. Australia, and then once I get Australia online, I'm going to start working on Brazil. So it really depends on where you live. Are there some ways to decompose a distribution? Like how Taylor series is applied to any continuous function. And I guess this is from John Lee. And I guess, John Lee, are you asking about a statistical distribution? And you don't know in advance what the statistical distribution is, so you try to break it down? I don't actually know off the top of my head. Someone asked if I would talk about LDA topic modeling, and I will keep that in mind. Oh, and hooray! It's my friend from Switzerland who's just joined us, and they said, I made it to the stream. Yay! Thanks for being an awesome teacher, Josh. Hooray! Well, thanks for joining us. That's made my day. So John Lee clarified a statistical distribution. Yeah, I unfortunately I don't know the answer to that. Not with a really cloudy brain right now. This is not maybe the best AMA that I could do because I'm like, my brain is only half here. Anyways, so with that said, I want to thank everyone for being here. And I really appreciate you guys sort of bearing with me while we prototype these new StatQuests and help me kind of work out some of the kinks and see what's clear and what's not clear and maybe what needs to be explained a little better. Hopefully you guys all got something out of it. And so with that, I'm gonna play a little silly song, and we'll conclude our day. Oh, wait a minute. Somebody asked about Gaussian mixture models. Yeah, so Gaussian mixture, my understanding of mixture models are, what they are, if you understand linear models, just regular old linear models like linear regression and multiple regression and ANOVA and t-tests and all those things, if you understand linear models, mixed models are basically how to do very similar things but with less data. And that's sort of the essence of the mixed model, is instead of validating things with data, you just make assumptions about how things are related and sort of what's going on. So, and those assumptions, when you make an assumption, you don't need data to back it up. It's just an assumption. So mixed models is basically linear models with assumptions that allow you to get away with using less data. That's my understanding of mixed models. And I could be totally wrong, but I'm pretty certain I'm right. So thank you for joining me today. It's been super fun. Hip, 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 hooray. StatQuest. All right. Thank you very much. I want everyone to have a great week, and I'll see you in 2 weeks.